Deep inside the hollowed-out Karst limestone mountains of Guizhou sits a massive vault. Hidden behind armored blast doors and strict military-grade security checkpoints lies a concrete bunker. The only sound inside this vast white space is a deafening, intense industrial roar. Millions of gallons of water are rushing violently through high-pressure stainless steel pipes. This is the Tencent Xisuan data center, an incredible multi-billion-dollar supercomputing fortress. Engineers excavated this facility into 5 interconnected mountain tunnels covering 30,000 square meters. To power China's massive artificial intelligence boom, next-generation microchips have hit a thermal wall. If these underground cooling loops stop for even 30 seconds, the system collapses. Millions of dollars of hyper-advanced hardware will literally melt into useless silicon slag. This is the hidden reality of the race to keep AI alive. China's domestic artificial intelligence surge is hitting a brutal physical barrier. The problem is not software code, but the raw physics of heat. Top-tier computing processors are drawing more electricity than ever before. Next-generation clusters consume and must dissipate an incredible 130 kilowatts per rack. This extreme energy is concentrated within a tiny, tightly packed server cabinet. Because of this heat density, traditional air-cooled data halls are completely obsolete. Air is a natural molecular insulator and a terrible conductor of thermal energy. Pushing forced air over hot, silicon chips caps the convective heat transfer rate. The physics threshold fails to pull heat away fast enough from the die. To cool a modern 100 kilowatt AI rack with air requires an insane volume. Fans would need to push nearly 16,000 cubic feet of air per minute. But fan power consumption scales cubically with the volumetric flow rate. This is governed by the physics formula, where power scales with flow rate cubed. Moving air that fast requires more electricity than the supercomputers use to calculate. The air boundary layer stalls, creating an insurmountable thermal wall inside the cluster. Without liquid intervention, the chips will rapidly throttle and suffer permanent physical destruction. To survive this thermal wall, China is burying its processing power deep underground. Architects chose the unique Karst limestone geography of Guizhou for a strategic reason. The massive mountain peaks act as a natural, absolute thermal shield. Thick limestone covers protect the server halls from extreme surface weather and solar radiation. The caves preserve a highly stable subterranean temperature and humidity baseline year-round. The mountain also shields the processors from potential military electromagnetic pulse strikes. But building massive data tunnels inside karst formations requires extreme civil engineering. Limestone mass is naturally prone to deep structural fractures and sudden water seepage. To stabilize the vaults, teams seal the walls using steel fiber reinforced shotcrete. They drill deep and secure the rock mass with high tensile steel bolts. Geotechnical engineers evaluate the cave stability in real time using complex empirical systems. They calculate safety margins using the Q system and rock mass rating metrics. This meticulous support prevents cave-ins under the immense weight of the mountain. It builds an absolute blast-proof vault. But the internal heat still requires a weapon. To cool down these advanced chips, engineers deploy a precise liquid hydraulic system. Inside the caverns, they use a method called direct-to-chip cooling. Copper plates containing tiny microchannels are brazed right onto the bare silicon die. A liquid coolant flows directly through these microscopic channels at high speed. This liquid contact unlocks a massive convective heat transfer coefficient. It reaches a stunning 15,000 watts per meter squared Kelvin. This allows the fluid to pull heat away 300 times faster than air. The liquid loop drops chip-to-coolant thermal resistance to just 0.013 degrees. To prevent rust, the loop uses a specialized organic acid technology fluid. This chemical mixture actively blocks microbial growth and internal pipe corrosion. But the ultimate cooling weapon inside China's fortresses is phase change immersion. Workers submerge entire server racks directly into pools of non-conductive liquid. They use advanced hydrofluorolefin dielectric fluids engineered to boil at 50 degrees. As the processors compute heavy data pipelines, the surrounding fluid begins to boil. This nucleate boiling utilizes the immense latent heat of vaporization. For special Chinese fluids like TMC49, this equals 93 kilojoules per kilogram. The intense heat converts the liquid into a fast-rising vapor. The hot vapor rises up to hit cold condenser coils inside the sealed tank lid. These coils are cooled by ice-cold fresh water pumped from deep mountain reserves. As the vapor touches the cold coils, it surrenders its hidden thermal energy. The gas instantly condenses back into liquid and falls down like artificial rain. This passive cycle repeats indefinitely without using a single mechanical fan. It slashes pump electricity costs to zero while keeping the AI cluster perfectly chilled. Feeding these massive mountain caverns requires a giant amount of electricity. A single computing block can easily pull 100 megawatts of power. High-voltage grid power must be stepped down to keep cables manageable. Traditional facilities use massive rooms filled with chemical backup batteries, but China's advanced fortresses are eliminating these chemical battery rooms completely. Inside the tunnels, Tencent uses a brand new power design. They combined a high-voltage direct current loop with direct mains power. This system runs at 240 volts with maximum efficiency. In normal times, power skips extra equipment to prevent energy loss. The direct current setup only triggers when the main grid fails. This trick cuts necessary power equipment space by 45%. It pushes overall power efficiency to a world-class 98%. It simplifies the safety network from a complex double chain to one. But without batteries, how does the system survive a sudden blackout? The answer lies inside heavy, vacuum-sealed kinetic flywheels. These mechanical batteries use massive rotors made of forged steel or carbon. The rotors spin at a blinding 37,000 revolutions per minute. Magnetic parts hold the spinners in place to stop mechanical wear. When the outer power grid buckles, the wheels keep turning. Their rotating physical mass acts as an instant power bridge. This kinetic momentum buys the facility a vital 10-second window. Inside that 10-second sprint, industrial backup generators must fire up. The engines stabilize their frequency and engage powerful mechanical clutches. They assume the full computer and cooling load before the wheels slow. This high-speed handoff keeps the entire mountain fortress online without stopping. This massive underground network carries a dangerous, hidden structural vulnerability. Inside the deep tunnels, engineers face constant mechanical fragility. High-pressure plumbing lines experience severe thermal expansion cycles. These continuous temperature shifts expand tiny defects inside the pipe connections. Over time, micro-leaks can develop, causing immediate electrical short circuits. A parallel hydraulic threat is a phenomenon called pump cavitation. This occurs when fluid pressure drops, creating tiny vapor bubbles. These bubbles violently collapse, destroying pump impellers and cutting flow. If the primary coolant flow drops to zero, disaster strikes. The processing chips shift from a stable 41 degrees Celsius. Without liquid running through the channels, temperatures explode instantly. Advanced chips utilize a strict automated protection countdown clock. At 83 degrees, the processor begins thermal throttling. At 85 degrees, workload migration safety protocols activate. At 90 degrees, the system executes an emergency hard shutdown. Under full calculation load, this entire process takes 23 seconds. This critical window is shortened by a semiconductor leakage penalty. As silicon temperatures climb, the internal leakage current drives up. This extra current forces chip power consumption up by 37%. It triggers a dangerous, compounding thermal feedback loop. Rising heat generates more current, which accelerates the melting process. To model this destruction, engineers use an empirical trendline formula. For a high-density 100 kilowatt server rack, the math is terrifying. The internal temperature spikes by nearly 5 degrees every single second. If a backup generator experiences a minor 10-second delay, the server cabinet temperature explodes by 50 degrees Celsius. This sudden heat wave triggers localized thermal runaway almost instantly. It can permanently destroy a multi-million-dollar artificial intelligence cluster. This extreme fragility makes sub-10-second power backups non-negotiable. China is building these data fortresses at an unbelievable speed. This construction is part of a massive national infrastructure plan. The strategy is officially called Dongshu Xisuan. This translates directly to Eastern data, Western computing. The country's massive tech empires are based on the coast. Companies in Shanghai and Shenzhen generate huge pipelines of data, but keeping supercomputers on the coast creates massive power issues. Coastal electrical grids are already crowded and heavily stressed. So, China is moving the heavy processing work away. They send the raw data thousands of miles inland. The information travels instantly to the mountains of Guizhou. Here, natural cold rock environments handle the cooling, heavy lifting. This network creates a unified, continent-spanning processing brain. The race for artificial intelligence is no longer just about software. It has transformed into a heavy civil engineering war. The true battlefield is fought with plumbing, rock, and concrete. China's mountain data fortresses have completely rewritten the rules. By burying supercomputers, engineers successfully defeated the heat wall. They turned brutal geological features into ultimate cooling weapons. This effort anchors the historic Eastern data, Western computing blueprint. It systematically shifts processing burdens away from wealthy coastal grids. The empty mountains of the West are now data strongholds. Billions of yuan continue pouring into these cavernous server arrays. This infrastructure ensures China's computational independence for decades to come. As algorithm demands grow, these vaults will only burrow deeper. The massive underground computing loop is officially secure, and the physical limits of silicon have been beaten. China has successfully engineered a blast-proof, hyper-chilled digital engine. The rules of global technology infrastructure are changed forever.